So, welcome to this lecture in which I will derive the closed for expression of outage probability for Rayleigh fading channels, and will also perform Monte Carlo simulation and see whether the results match or not. Uh, for reference videos in my playlist of wireless research, you can check out the lecture number 9 where outage probability using a random variable has been discussed in detail. That is what we are going to use in this lecture. Uh, this is our model that we are using every time, that there is a symbol X that is being transmitted by a wireless user across a fading channel. That is, the fading is denoted by H, the AWGN is denoted by noise N, and the received signal is Y. So in this case, the SNR computation, SNR is signal to noise ratio, is done using this expression. The signal Y is XH plus N. uh, we take these to be the voltages, and therefore the powers become the square of it, proportional to the square of it. So we take the signal under fading is this component, and this power is expected value of mod x square and mod h square. So this is through the fading channel, the power, and the power expected value of mod x square. In this derivation, or in this computation, we'll assume that this is P1, and this N is modeled as noise, additive white Gaussian noise, having a variance of sigma n square, and therefore the signal to noise ratio is signal power upon noise power, and it happens to be denoted by gamma, and expected value of mod x square, mod h square upon sigma n square. So, having computed the signal to noise ratio, what is the outage probability? We can see that the outage probability depends on mod h square and sigma n square, and both of them are random variables. So we define the outage probability to be the probability that the instantaneous SNR gamma falls below a predefined threshold SNR gamma DH. Uh, if our gamma is P1 mod h square upon sigma n square, we can assume P1 upon sigma n square to be average SNR gamma bar into mod h square. So our instantaneous signal to noise ratio is average signal to noise ratio multiplied by mod h square. So we'll where more bar of gamma is P1 upon sigma n square. So the outage probability is gamma, probability of gamma less than gamma th, which means this probability, and which further means that it can be calculated using the CDF of the channel. So if I have the CDF of this gamma, then I will calculate this CDF as gamma th, because we know that the CDF of gamma is nothing else but the probability of gamma uh, less than gamma th. We can compute CDF using integration of PDF denoted by small f suffix gamma y of dy. So we will integrate from minus infinity to gamma th. In this case, we are assuming that there is Rayleigh fading, and for this, we assume that the PDF of Rayleigh fading of signal to noise ratio gamma as a function of y is 1 upon bar gamma exponential of minus y upon gamma, and it exists only for positive values of y. Therefore, if I used our definition of outage probability, the probability of instantaneous signal to noise ratio falling below threshold SNR is CDF computed at gamma th, which is integration of minus infinity to gamma th fy dy, where we'll use this Rayleigh distribution PDF. And you can also assume that the integration will now not for all values, but will only be for positive values. So integration not start from minus infinity, it starts from 0 to gamma th 1 upon gamma exponential minus y upon gamma bar dy. This integration is very simple. It is e raised to the power minus a x with respect to x, which is e raised to the power minus ax upon minus a. We put the limits 0 and gamma th, and we get 1 minus exponential of minus gamma th upon gamma bar. Then we'll define the average power P1 underscore dB from 0 as an interval of 5 to 40. So it goes from 0 to 40 with a gap of 5 dBs each. These are in dB, so I will calculate this in linear terms. It will become P1 is equal to 10 raised to the power P1 underscore dB upon 10. So this will be my average power. And I will also define a variable length len, which is the length of P1. So how many values are there? So these are 11 values. We'll define the threshold SNR gamma underscore TH as 10 raised to the power 2 upon 10, which means the threshold SNR in dB is 2 dB, and I have converted that into dB, not linear scale in this. So our exact probability we have derived as 1 minus e raised to the power minus gamma TH upon SNR. So this is my exact outage probability expression. So this is what the derivation yielded when we computed it. Also, we will like to perform the Monte Carlo simulation, for which first of all I will generate Rayleigh random variables. So for that, I will first of all assume that how many random variables I am taking. So suppose for instance I am taking only 10,000. We generally require this to be 10 raised to the power 6, a very large number. So we'll use a for loop, and we'll first of all h1 or HSR we will define, which is rand n 1 comma 1 comma size plus 1 I asterisk, which means that it is a complex. This is making it the complex term, the imaginary term, rand n 1 comma 1 comma size upon square root 2. So this is my uh, exponential Gaussian random variable. We require it to be mod h square. So for that, I will in one loop I will assume it to be absolutely mod h underscore sr square. So this is mod h1 square, if you can understand, and I am multiplying this with every average SNR value. So I'm taking a loop of P2 from 1 to the len, how many P1 values are there, and I am storing that for each loop, and then I am saving that into a variable named gamma underscore 1. So this generates my gamma underscore 1, which is Rayleigh random variables. Now these variables I will show in workspace also have the dimensions that will match to our Monte Carlo simulations. Now I'll perform my Monte Carlo simulation, in which what we do, we actually perform the exercise n number of times where n is very large, and then average out with the n. So how do we do that? We first of all assume that outage 1 1 is all zeros of length of dimensions 1 comma the length of p1, which is also len. So we perform a nested looping. So first of all, we'll use one variable p1 from 1 to length p1, and we'll use kk1 to from size 1 to size. This size is actually the number of variables that we are using. So we have already generated our gamma underscore 1, which are all random variables. I am now taking the corresponding to SNR and corresponding to the Monte Carlo simulation. So this P1th and KK1th, this is row, this is column, where a Rayleigh distributed channel gain is stored as SNR1, and we check that this gain is less than threshold SNR or not. So we again use a small for loop when I'm using loop for gamma th. If there are multiple gamma th, I can use this also. In our case, there is one gamma th, and we compute what is the probability that if SNR1 is nothing else but the random variable corresponding to P1th and KK1th is smaller than gamma th of the indice and the indice. But indice in this case is not important. So that we will, and if this happens, if the SNR is smaller than this threshold SNR, then I will increment this was all zeros, I will increment this by 1, otherwise not. And this we will store in outage underscores values 1, है for all the SNRs. So this, as it is added by 1, it is stored here. And in Monte Carlo simulation, what we do, we end all, first of all, this if is ended, then this for is ended, then this for is ended, and another for P1 is ended. And finally, the Monte Carlo simulation results is basically whatever I have stored for each SNR, I will divide by the number of samples that I have taken, which means that we will take the average out of this. So I will show how this code works in MATLAB also. So suppose, first of all, the exact analysis. First of all, the average SNR values. So if I only run this selection, then you can see that I have P1 dB is 0, 5, 10, and 40, and the corresponding linear SNR are 10 raised to the power this thing. After that, if I run till this point, then you can see that the exact outage probability is there. So this is the exact outage probability, 1 minus e raised to the power minus gamma th upon average SNR. You know, so this is like this. Now we perform the Monte Carlo simulation. Size, suppose I am taking size of 10,000. I can also increase that. So say 10 raised to the power 5 I have taken, and the same code that I have shown. So first of all, I will run up to this point only, so that you can see what happens to gamma underscore 1 th. So this is gamma underscore 1. This is 9 comma 10 raised to the power of 5. So these are all 9 values. The 9 values are corresponding to this. What I have performed here is that I have mod h square into p1 I have done. So I have stored this my random variables which are proportional to the powers of the signal to noise ratio. It's not only mod h square, it's mod h square multiplied by p1 for each SNR. And then I perform my Monte Carlo simulation. I declare this outage 1 1 to be all zeros, and then I perform this. So what happens if I run this part only? My Monte Carlo simulation runs and simulation is over. So I have some values which are stored in outage values 1. What are these outage value 1s? These are all the values that have been computed across it, but across the loop for size. Size means for 10 raised to the power 5 times if I use the SNR values which are proportional to the SNRs and are following Rayleigh distribution. So if I do all that and now I take the average, which means we perform the average of it by dividing with the size, we get p out sim, and we are taking only the values of all rows and all columns. And if I just I can show you that this, you can see that these are the values that we are getting through Monte Carlo simulations. These are the values. So I will only plot these values. uh, I've taken all rows and all columns on line number 34. It's because sometimes the values are zero, so I need to do that. And now I can plot it on semi-log y scale, both exact and the Monte Carlo simulation results. So if I can do that, you can see that this is my result. The outage probability is on the y-axis, and on the x-axis I have average SNRs. I have not labeled it. The asterisks that are there are the results of the Monte Carlo simulation, and the straight line is basically the actual values. The SNRs, average SNRs are 0, 5, 10, 15, 20, like this. You can see the asterisks are lying on the line, on the straight line. So exact is matching with the Monte Carlo simulation results. This is how you perform this analysis, that you firstly derive an expression using the PDF or CDF through random variable results, and then you verify this using Monte Carlo simulation average sum, the rule of the theorem of averages, that if we take a large number of samples, we average it out, we get the same things. So thanks for watching this video. I hope this video has helped you to understand the basics of how Monte Carlo simulation can be used to corroborate with the exact results in wireless fading channel analysis. Thank you.